Welcome, welcome, my lovely students. So what we're going to look at this week is radicals, and there is a bunch of different little things we're going to look at. Then the other thing for this week is a review. So on Thursday, please show up to class. We will discuss the review. I will be posting it tonight. The midterm is going to be a week from tomorrow, so in 8 days, and part of it is going to be take home. So come on Thursday with your questions about the test and about the review. Now for radicals, I have to say it at least once. That way, because I'm a child of the 80s and the Ninja Turtles are awesome. Were awesome. I don't watch today's Ninja Turtles. All right. So our first definition is an nth root. The nth root of A is equal to B if B to the n equals A. Yay, that's nice, and what the heck does that even mean? All right, there's a caveat if n is even, if the root is an even root like a square root or a fourth root, then the inside, the A needs to be positive and the B needs to be positive, or else we don't get a real answer. We get some weird imaginary thing. If you're looking at any of the explanations, these are the fancy names of the individual pieces that I never remember to use, so put it there just in case. So here's what we're looking for on these radicals. So we have the cube root of -125, the sixth root of -64, and the -sixth root of 64. So when you are looking at breaking down these kind of radicals, what you want to find is cube roots require groups of 3. So some number to the third power that is equal to the inside. So that's what the definition up here is really getting at. The cube root of -125 is going to equal B, whatever B is, if I can come up with a B to the third that equals -125. Now you don't have to like poof magically find the right B. A lot of these, especially what you'll see in the questions later on, if you just break down the number into its prime factorization, then you can look for the groupings that are required by the radical. So a cube root requires 3 of the same thing. A sixth root is going to require 6 of the same thing. So -125. So I'm going to kind of ignore the negative for a second. Just focus on 125. That ends in a 5. It is actually 5/4. So 125 is the same as 5 to the third. But we had a negative sign. So the question is -5 to the third the same as -125? So let's write that down. So a negative times a negative is positive, and then times one more negative is back to negative. So this is indeed -125. So our answer then, the radical, equals -5. All right, so I wrote B and C, but really these are a pair that go together. So you should notice that the difference is where I put the minus sign or the negative sign here. So C, the negative sign is hanging out on the outside. That just means whatever result we get from the radical, that negative is going to be part of the answer. So our answer will be negative. For B though, more problematic. A, I could cube root -125 because I can cube root a negative. The cube root of -1 is -1. But the fourth root of -1, not real. The square root of -1, not real. And if your brain goes, oh, that's the I thing, yes, we will get to that in a week or so. Not today and not on the midterm. So any even root, I can't raise a number to an even power and get a negative result without venturing into complex numbers. So here, The sixth root of negative 64, what I'm asking is, what b number to the sixth power is going to equal a negative 64? No real number can I raise it to an even power, because all the negatives will pair off for whatever number I try. So we're going to go with a no real answer. And now over here, the negative on the outside, certainly I can calculate this. So what I really need to know is 64 is what number? Now for the prime factorization, you don't have to stumble across the correct, there's no right or wrong way to do these as long as you break all the numbers down until you get to primes. So you might look at 64 and go, oh, that's 8 and 8. And we can split it that way. You might just say, hey, I know that's even, so 2 is going to go in there. And then you just start dividing by 2s till you run out. Also works. You will get the same result as long as you continue down to the end. So 8 is going to be 4 times 2. And then the 4 is another pair of 2s. So let's count them up. Now, when we look at this, we are only looking at the numbers that are at the ends. So those numbers I just circled are the same as 64, all those numbers multiplied. The 4 and the 8s that come before are not part of this because we broke them down further. So it has to be an endpoint number that doesn't break anymore that we're going to count. So 64 is the same as 2 to the 6th. But we were doing a 6th root. So since 64 is 2 to the 6th, the 6th root of 64 is just 2. And with the negative. Now I'm going to include the next part. These are fractional exponents. So this falls out of our exponent rules. So when I have something squared or something to some arbitrary power, and I want to raise it to another power that is going to cancel that out. So if I have like a to the 3rd, or here we'll do 4 since we haven't done a 4th root. So a to the 4th equals, we'll say 16. So I want to think, what power am I going to put here and thus put on the other side such that this result is a? That'll be a equals 16 to whatever crazy power this is. So 4 times what number equals 1? That is what we're asking now. And if we divide the 4 over, we have what number equals 1 over 4? That is what our number equals. But I know as a concept, to cancel out and undo a 4th power, I use a 4th root. So this 1/4 exponent is also the same as the 4th root. So our a here is equal to whatever 16 to the 1/4 is, or you could write it as the 4th root of 16. But in this case, the 4th root of 16 actually does continue to work. The nice thing about the fractional exponent is that is how you can enter these on the calculator. Now, for some of the calculators, they can get a little annoying about this. So I always like to put my starting number in parentheses, and then I will try like this in a TI. So raised to the 1/4. Sometimes it'll do that, especially if the first number in the fraction, the numerator is a 1. If the numerator is a different number, you might have to break it up. So if this was instead of the 1/4, it was the 3/4, I might end up having to do 16 to the 1/4 and put parentheses around that and then raise that to the 3rd power if it was the 3/4. Or I could do the 3 inside and the 1/4 outside. The order there doesn't matter as long as they multiply to 3/4, which is what we have going on here. When I have a to the 4th to the question mark, That is 4 times question mark when I reduce it. And then I know I want it to equal 1. I'm trying to figure out which question mark would make it equal 1, and it was 1/4. So that is why we have this definition here, that 1 over n is equal to the nth root of a, and if I have it as a fraction, m over n, m stays as an exponent on the a, the over n fractional part becomes a root. Or you could just leave it as the fraction m over n. So our old exponent rules still apply here. So if I've got the same base and I'm multiplying them, I can just add the exponents. Oh yeah, see, they've got 16 to the 3/4, and here they said you could do the 4th root first and then cube the answer. Totally works. Or you could cube the answer first and then do the 4th root of that. Also works. Honestly, if it's all numbers, if you're comfortable putting it on the calculator, I'm totally fine with you guys using the calculator to solve it. All right. So we got a couple of simplification questions, the lovely vague directions. So I put -27 over 125, that is raised to the 1/3. 64 is being raised to the 1/2 power. And then I have -8 in parentheses to the 4/3. So for the fraction, sorry, you can think about it a number of ways, but the radicals are like exponents. If I had a fraction raised to the 3rd power, then I'd have the numerator to the 3rd over the denominator to the 3rd. I could break it across the division, so I can do the same thing here. So I want to know, what's the cube root of 27? What's the cube root of 125? We just did 125, that was 5. So I have a negative, and I know now there's a 5 on the bottom. If we look at 27, that is 3 times 9. That is 3 3s. So the answer result there is -3/5. Now they won't all work out nicely on the homework, but most of them will. Like to the point that if I get a decimal, unless I'm working on a word problem, I question it. All right, 64 to the 1/2. So that way was more hand wavy what we did with the fraction. For this one, what I want you to consider is, what if you don't pick the right number in the right grouping here? So 64 is 8 squared. It is also 4 to the 3rd. And it is also 2 to the 6th. So I'm going to put 2 to the 6th in there. Since that's the same as 64. So now I have 2 to the 6th to the 1/2. So the to the those exponents only have the quantum of math between them, so they are close enough to multiply. So 6 times 1/2, or half of 6, is indeed 2 to the 3rd, which comes out to be a lovely 8. But if you remember, 64 is just 8 times 8, so it's 8 squared. Then the squared power and the 1/2 cancel off. Now the last one, anytime I see a negative numbers, especially in parentheses, I always kind of pause and, is this going to be real? So I have the 4/3 power. So you now have to remember which of those is the root, which of those is the exponent. So I like to remember, we say 4th root, 5th root, and then the 5th power, the 4th power. So the fractions go with the radicals. So this is really asking, what's the cube root of -8 that you then multiply times itself 4 times? So again, I'm going to do it kind of similar to B. So -8 on its own has a -1 times a -1 times a -1 times whatever numbers make up 8, which we did just do. So this is actually the same as -2 in parentheses to the 3rd and I raise it to that other exponent. And remember, power to a power, they multiply. And the 3's cancel, so we get -2 in parentheses to the positive 4th power. 2 times 2 is 4. 4 times the other pair is 4. So, whoa, sorry. Hit the touchpad. So this is positive 16. Whole lot of work there. All right, I'm going to pause it and then pick it back up.